Since 2018, Elon Musk has been hinting that the newest Tesla Roadster will use rocket thrusters to launch the car at previously unheard of speeds for production vehicles. Then, in February 2021, Elon appeared again on Joe Rogan's podcast and gave more details on the planned rocket car hybrid, saying it may even be able to hover 1 or 2 meters above the ground. Now, is this just Elon Musk being the eccentric billionaire we have come to know and love, or is a flying rocket-powered roadster actually possible? There seems to be a lot of differing views around this, so let's do some rocket science and find out if this is physically possible. Also, if you like this video, don't forget to hit the like button below and subscribe if you want to see more videos in the future. So first things first, let's look at what we know and set out the assumptions made throughout this video. Let's face it, a rocket-propelled car is not going to work well on a busy road, or probably any road for that matter where there may be someone or something that doesn't want to get hit by a 1,500 mph jet of gas. So let's assume this is just for drag strips and race courses. Oh, and that money is not an object. Also, this video is going to be a pretty high level look at the system, meaning things like losses in the pipes and exact values, where they are complex to calculate, will be ignored or simplified. Before looking at these, it is good to see what a cold gas thruster actually is, as that is the type of rocket Elon Musk says the Roadster will use. A cold gas thruster is a type of rocket engine that uses the expansion of a pressurized gas to generate thrust. This gas could be many things, such as nitrogen, helium, or even normal air, which is a mixture of lots of them. Elon Musk has said that the Roadster will use air from onboard compressors. However, as we will see later, this is probably not the most practical option, so we will instead assume that we are using compressed nitrogen gas. The compressed gas is in a pressurized tank, and as it is released through a valve, it expands and produces thrust. This makes cold gas thrusters much simpler, cleaner, but also less powerful than other rocket types. Because looking at the nozzle design is beyond the scope of this video, we'll assume we have an ideal nozzle which perfectly expands the gas. This means that the pressure of the gas here, at the exit of the nozzle, is the same as the pressure around it in the atmosphere. This makes the whole system much easier to understand without sacrificing too much accuracy. So from what Elon has said, we know the rocket should produce 3 tons of thrust on Earth, which is equal to 30,000 newtons of force, which incidentally would be enough thrust to lift the whole car off the ground, as it is expected to weigh around 2 tons. And to allow the Roadster to hop off the ground or accelerate to over 100 miles an hour, we'll probably need this for, let's say, 5 seconds. With this, we can start to size the rocket thrusters and see if this is actually possible. You may have seen videos about rockets with people talking about specific impulse, which is a good measure for seeing how much thrust certain types of rocket propellant can give you per kilogram. So a high specific impulse means you get a lot of thrust per kilogram of fuel. However, in this video we are going to look at how fast the gas comes out of the rocket, known as its exit velocity. Because we are assuming we have a perfect nozzle, these values are easily related. Personally, I also find exit velocity much more intuitive and easier to understand than specific impulse. To find out how much thrust our rockets can give, we'll use a variation of the classic force equals mass times acceleration, or Newton's second law. But instead, we will say the thrust force is equal to how much gas is being shot out of the rocket, known as the mass flow rate, times how fast it is going. So we know the force needed, which is 30,000 newtons, but how do we know how much gas is coming out and how fast it is going? To answer this, we'll first work out the speed of the gas. Now, this uses a pretty horrible looking equation, but it's not important to understand fully, so don't worry if you don't, and stick with me. The key things to know here are that with this equation, you can work out the speed of the gas coming out of the rocket if we know its temperature, pressure, and some information about our chosen gas, which is nitrogen. Now, because the gas absorbs a lot of heat from the pressurized tank as it expands out, the cold gas thruster can get very cold. So for this video, we'll use minus 100 degrees Celsius or minus 148 degrees Fahrenheit. And for the chamber pressure, we'll vary it to see how this affects the speed of the gas. This graph shows the results. and it is clear that if we keep the tank pressure above a few hundred psi, we should be able to keep the gas going around 500 meters per second or 1100 miles per hour at all times. It will be quicker to start with before the thruster gets cold, but this gives a good overall estimate. So now back to our original formula. So we know we need 30,000 newtons of thrust from a jet of gas going 500 meters per second. From this, we can work out that we need 60 kilograms per second of nitrogen gas. So for 5 seconds of thrust, we'll need a total of 300 kilograms of nitrogen. Well, that sounds like a lot of gas. And it is. So is this even possible? The way this would be stored is in composite overwrapped pressure vessels. These can hold very high pressure gas up to around 700 bar or 10,000 psi, which is the value Elon Musk said the gas will be stored at. For reference, this is also the pressure that hydrogen is kept at in the Toyota Mirai. With this information, we can see how many gas tanks we will need. But before we do that, there's one more thing we need to look at. See, the gas released from the pressure tanks are controlled by valves, and these need to be able to allow enough gas to go through them at all possible operating pressures. To keep the same amount of gas flowing the whole time, the valves need to open wider as the pressure drops. Think of this like lots of people trying to fit through a door. If the door was bigger, people behind wouldn't have to push so hard or apply as much pressure to get the same amount of people through the door. So why is this important? Well, as the pressure in the gas cylinders gets very low, the valve would have to open extremely wide to let the needed amount of nitrogen through. For valves, a value that is called the valve coefficient, or CV, is used to say how much gas or liquid will pass through them under a certain situation. As the pressure of the nitrogen tank decreases, these valves will have to operate at a higher CV value to make sure enough gas can go through it. To show this, I've used an equation that works out the valve coefficient depending on the required gas flow rate, its density compared to air, and the tank pressure. Though it should be noted, for the flow rate of the gas, I have divided it by 4, as we will assume 4 small tanks are going to be used. Like with exit velocity, I have plotted this for different tank pressures. We can see that the valve coefficient gets pretty big when the pressure in the tank goes below a couple thousand psi, unlike the exhaust velocity that only started reducing after a few hundred psi. If we say Tesla can source some very high performance valve tech from their convenient friend SpaceX, we can roughly estimate the valves would be able to operate at 10,000 psi with a valve coefficient of 30. This would mean that although we are using 10,000 psi tanks, we wouldn't be able to drop the pressure below around 2,000 psi. Otherwise the valve would be too small to let enough gas through to give us the thrust we need. Meaning we have 8,000 psi or about 540 atmospheres of pressure to work with. So why do we care about this? Well, this is how we now work out the size of the high pressure tanks. We know we have 540 atmospheres of usable pressure, and that we have to store 300 kilograms of nitrogen, which is equal to 240,000 litres. Because this 240,000 litres will be pressurised 540 times, it means it will only take up 450 litres of space, which is how big the nitrogen tanks will have to be. By looking at a company called Steelhead Composites, a 112.5 litre tank could weigh around 85 kilograms and have the dimensions of 1.2 meters long and 0.45 meters diameter. By looking at this very rough picture, it seems like it should be possible, with some innovative thinking, to fit in all the required gas tanks into a Tesla Roadster that has no back seats. Though I expect Tesla engineers could do a much better job at this than I have. So from these rough calculations, I think it shows that the idea of a rocket-propelled car that can even hop off the floor and fly for a second or two, as crazy and impractical as it seems, should be physically possible. I've seen a lot of skepticism about this car, so I thought this basic analysis would be interesting to put into the mix. This is by no means conclusive, but it makes me very interested to see what Tesla does. My main concern for this idea is the refueling. Elon said that the car would compress air from the atmosphere and use it to refill the tanks on board. But as pointed out in a video by Thunderfoot, this would require a multi-stage compressor and would be very slow and too heavy to fit into a vehicle. Therefore, I imagine an external refill system would be required, much like those for hydrogen fuel cell cars. Also, as previously said, the gas could not be air. This is because the moisture in it would freeze due to the cold operating temperatures of the thruster. This moisture could be removed, but it would add further size and complexity to the system. In total, the tanks and gas would weigh around 650 kilograms when full, or 350 kilograms when empty. This is a lot of extra weight, so maybe some of the batteries may be removed and others rearranged to improve the weight distribution in the car. Overall, it sounds like a fun project to work on that could, from my calculations, be technically possible. But we'll have to wait and see what happens. Thank you very much for watching this video. I hope you liked it or at least learnt something new. This was a really interesting video to make, so I'd love to hear your comments down below. And if you liked the video, please leave a like, and if you want to see more, then please subscribe. And thanks to all of you that have already subscribed, as we're now over 33,500 subscribers. I'm aware that the calculations in this video were simplified and weren't perfect, but I thought it might add something interesting to the current discussion. This is by no means a prediction of what's going to happen or what I think should happen, but I think it was interesting either way. But that's all from me. Thank you so much for watching, and I'll see you in the next video.